Hello, and welcome to the Week 4 set of lectures of Digital IC Design with Dr. Mark Narden. In this week's set of lectures, the high-level outline is I'll first introduce the concept of ALUs, that's arithmetic logic units. Then we'll go through various functions that you might see in ALUs. The main functions that I'll be going through are adders, basically multi-input. So if you have an A input and a B input and carry, and then go through comparators, shifters, and I'll also discuss multipliers in this week's lectures. So basics of ALUs. ALU stands for arithmetic logic unit. This is a large block of combinational logic that can perform a number of different logic functions based on the inputs that you supply to it. So in general, we provide two data values, and each of those data values can be multi-bit. So you might have the values of A and B are numbers that have multiple bits to them. So it could be 8-bit, 16-bit, or more for each of the two values of your data, A and B. Then you also send in a control input, which typically is also multi-bit. We'll call our control input S, selecting what we're going to do in the ALU. And the value of the multi-bit control input determines what logical function you perform on the data inputs in order to produce an output value that comes out of the ALU, which we'll call the output value Y. Again, is also multi-bit. And the number of bits in Y is typically equal to the same number of bits in A and B, and A and B also have the equal number of bits. Now, I mentioned you have a control value coming in. Just as an example, if you have a 3-bit worth of digital control value coming in, that gives you 8 possible combinations of what the number can be. So a 3-bit control value can give you 8 possible logical functions that the ALU can do, and like a 4-bit control value would give you 16 possible functions, etc. The input data could be any number of bits, but like I said, the number of bits of A and B and your output Y are all going to be the same number of bits, whatever you choose. For early ALUs in early microprocessors, you might have had just 4-bit or 8-bit ALUs. Then over time, it progressed to 16-bit, then 32-bit, and in most modern CPUs typically use either 64-bit or 128-bit ALUs. And again, that's the number of bits of the data values A, B, and your output value of Y. Some of the common functions that an ALU performs can be doing an add, a subtract, incrementing and decrementing are all kind of in the same category. Then there's also what we call bitwise functions. So like AND or an or a ones complement could be you take the bits of A and B, and for each bit, like the 0th bit, you AND A and B together, or A and B together, and you do that on a bit by bit basis all the way through the total number of bits you have. So you can either perform the AND or an or an XOR function bitwise on A versus B, or a ones complement would be taking either the value of A or the value of B and inverting it, so bitwise inversion, 1 to 0 or 0 to 1. Those are kind of the bitwise types of functions that ALUs can do. And then there's other functions like shift and rotate, where you will take either the value of A or B and shift all the bits left or right, or basically rotate it around. So with a shift, you'll shift in a value either on the left or right, depending on if you're shifting left or right. With a rotate, you would take the value from one end as it's rotating or shifting out and rotate it back to the other end and rotate it back in. And then there's other more complex variations of each of these functions, but we'll just go into some of the basic functions today. Adders are an important function in modern microprocessors, and as such there's been a lot of work put into trying to optimize adders in various different ways. So there are many different variations on adders, and I will be going through those next. So this is just a quick outline. First we'll cover single bit addition, so just a single one bit of A and one bit of E, or one bit of data B and A adding together. Then we'll talk about multi-bit addition, and as part of that you have from each bit you get a carry value as well as the sum of the bits, and so we'll be talking about the variations on how the carry is handled. So there's a carry ripple adder, carry skip adder, carry look ahead adder, carry select adder, carry increment adder, and then tree adders, and there's various variations of those depending on what you're trying to optimize in your adder, both the layout and the delay of how fast you can do your addition. So let's start out with just looking how a single bit worth of addition, how that's performed. So you have, we'll start out with the left side of this this figure, where we're talking about a half adder. So this is a half adder is basically just talking about a single bit addition. So you have the data value of A and data value of B. You only have one bit that you're trying to add, and you also assume that we're not doing a carry in from any previous bit. So you just have bit A and bit B that you're trying to add together. So you have four possible combinations of inputs for A and B, 0, 0, 0, 1, 1, 0, and 1, 1. And then you have two outputs that we expect. One is the sum of A and B, and the second output is the carry. So depending on what values of A and B you have, you could get a carry coming out of your addition value. This goes back to simple addition. So if we look at, if you have a 0, 0, you have 0 for your carry and 0 for your sum. Everything's a 0. When you have a 0 and a 1 coming in, you will have a 0 carry, but your sum will be 1 because 0 plus 1 is 1. The same is true of 1 and 0 coming in for A and B. Your sum is 1, but you have no carry coming out. And then only if both A and B are 1, then you get a carry coming out. But with A and B both being 1, that particular bit will sum to 0 with a carry. Now, let's contrast that with a full adder. A full adder assumes that you have multiple bits that you're adding together. And so now, when we had the half adder, let's say if we had bit 0 of a 2-bit number, so we have a bit 1 and a bit 0. Bit 0 would potentially be able to use just a half adder, but bit 1 would have to look at A and B coming in as well as the carry from the previous bit coming in. And so now we need to look at 3 inputs, A, B, and C, C being our carry, and we still have the same 2 outputs, C out and the sum. So in this particular case, our sum is now going to be in XOR. So XOR function is if 2 inputs like A and B are both 0 or both 1, you get a 0 out. But if either one of them, but not both of them, are a 1, you get a 1 out. So you get a 1 if only one of them is a 1. So in the case of 3 bits coming in, again, you'll only get a 1 if one of those inputs is a 1. Otherwise, if 2 of them are 1, you'll get a 0. So any 2 of them are 1. Or in the case of 3 bits of an XOR, if all 3 of them are 1, you'll also get a 1. Because in effect, an XOR function with 3 inputs, you do an XOR of the first 2, and then the result of that, you do an XOR with the third one. And then for the carry, you only get a carry out if the majority of the 3 bits, A, B, and C, are 1, then you'll get a carry out. So if any 2 of them, or if all 3 of them are a 1, you'll get a 1 out. So let's look at how that resolves. So if A, B, and C are all 0, your sum and your carry are both 0. If A, B, and C, if only one of them is a 1, then you should get no carry out, because you need at least 2 of them to be a 1 to get a carry out. But your sum will be a 1. The same is true in the next case, where only B is a 1, so only one of them is a 1, so you should get your sum of 1 but no carry out. The next row there, you have 2 1s, so now you have a majority are 1, so you should get a carry out, but your sum will be 0 because you only have 2 1s, and so an XOR of 2 1s gives you a 0, and then XORing it with the 0 stays 0. The next one, since we only have 1 1, we get the same result as no carry out, but our sum is 1. And then the following row, again, we have 2 1s, so we should get a carry out, but since there's only 2, our sum will only be a 0. And then the same is true of the next row. We get a 1 and a 0. And then finally in the last row, our majority of 1s, so we get a carry out. And when we do an XOR of the first 2, we get a 0. XOR of the result, 0 and 1, we get a 1. And so we get 2 1s out if all 3 are 1. On the previous slide, we had gone through the full logic function of generating a sum and carry out. The equations for what those logic functions, the logic table tells you the result are shown here, where the sum is going to be the XOR of A and B and carry in together. So you could either do an XOR of A and B followed by the output of that being an XOR with carry in, or you could do a full XOR of A, B, and C together in one stage. And then carry out is going to be the majority of A, B, and C, which means that as long as the majority of those 3 bits are 1, so at least 2 of them, if not 3 of them, are a value of 1, you'll get a 1 out on your carry out. The lower left corner kind of shows logically what we're doing here. A 3-bit XOR function gives you your sum, and a 3-bit majority function gives you C out. Then on the right hand side is shown one possible way to create those 2 values. First of all, for this particular function, we need A and A bar, B and B bar, and C and C bar in order to create this for this method, this particular implementation shown here. So we have 3 inverters needed, and then the left-hand circuit shows us how to create your sum value in a single gate stage for the XOR function. So that is a way to do a 3-bit XOR in a single stage to get sum out. A different way we could have done it, like I mentioned before, is you could do a 2-bit XOR in one stage followed by another 2-bit XOR in a second stage. might be a little bit more delayed than a single stage. So this could be a way to do it in a single stage with a little bit quicker. The circuit on the right is a way to do a single stage 3-bit majority function to get C out. So this is possibly the quickest way to get a sum and C out in a single stage. If we go and add up all of the transistors for both of those stages, plus each of the inverters having 2 transistors each, you'll see that we have 32 transistors needed to implement this entire function. And so we'll look at how that compares versus some other methods to generate sum and carry out. So this second design for a full bit adder design for a single bit of full bit adder is if we go back and try to factor our S term, our sum term, in terms of C out to get one of the ways we can do it is the following equation. So we refactor it. If you go in the book, chapter 11, you can see how they did this refactoring, but I'm not going to cover that in the slides here. You can read that offline. We can see we can factor S in terms of A and B and C, or in A or B or C ANDed with C out not. So in terms of doing it this way, one of the benefits it gives us is our critical path of basically the logic function through the full adder is our carry path, because the carry goes from bit to bit to bit, whereas A and B are determined by each individual bit has its own A and B that are there before we start the carry. And so the carry having to go to the higher order bits, it has to go through all of the lower order bits first. So the carry is the critical path through the adder. So in terms of that, we want to speed up the carry as much as possible. So this particular way of doing it gives us a carry path that goes, we get a C out bar from this a little bit quicker than with the previous design. And the other factor in here, so the sum might take a little bit longer, but generally the sum is not the critical path because it doesn't have to go to the next order bit. So we want the carry out as quick as possible, and you can see we can get a carry out bar, and then we include a inverter, so we have carry out bar and carry out that can be used going into the next stage if we need a carry out bar into the next stage. Also, if you look at this particular design, since we only need A, B, and C, we don't need the inverted versions coming in. The total number of transistors needed for this design add up to 28 transistors, as opposed to the 32 that were in the design that we had for the adder design 1. Here I'm showing figure 11.4 from the basically chapter 11 of the book, just because it shows a little bit more detail of what we were talking about on the previous slide. So in the A, basically the circuit shown in A actually shows the logical function that we're implementing in a single gate for C out. The logical function that we had on the previous page, you can see you're doing an OR of A and B, and then along with A, B, and C, that AND OR function is what gives us the C out bar, and then that leads into the second stage that we're basically calculating the sum. And again, you can see C out bar comes out in a single stage. The sum needs to wait for C out bar to come out from this stage in order to generate the sum in a single stage plus the inversion. But again, the sum isn't typically the critical path in our adder, and so we get the C out bar pretty quickly in the single stage, which is what we care about. And then the part B of this figure is basically the actual guts of the stage that we were talking about, or that we showed in the previous foil. And then part C kind of shows us how we might actually do the sizing for this gate. And one thing that you can see here in particular that's critical is the very input where C is coming in on the very left hand side. You can see that's sized 8 and 4, whereas pretty much all the rest of the sizing of the cell is size 1. The reason for this is because like I said, the carry in to carry out is our critical path, so we want that to be as fast as possible. If we do larger gates for the carry in, which are size 8 and 4 for the P and NMOS, the speed going from carry in to carry out bar is going to be a lot faster than if we use minimum size gates. But yet, and the reason why we're using minimum size gates for the rest of it is because it's not in the critical path, and if we make it smaller, it will actually allow the C out to go out faster because there's less parasitic capacitive load on the C in to C out path, and we can make the overall layout size smaller for this overall gate by making the rest of it small. And like I said, since we don't really care about the speed of the sum out, we can make all of the devices relative to calculating the sum out a size 1. That way it minimizes our layout and maximizes our speed of carry in to carry out. So this is kind of an interesting way to do the design. Here's another figure from the book showing how you could do the actual layout for the two different designs that we showed on the two previous slides. Basically, the version A is if we were doing our adder design, kind of shown the way that we're typically doing layout in our labs, where we have our poly is vertical and we have the PMOS structures on the top, the NMOS structures on the bottom, and we basically kind of have the design flow from the left side of the circuit is on the left side of the layout here, and it kind of flows through to the right side of the layout. So in this design is more typical of how we would probably do it in the lab. Basically, this foil, or this particular figure, is showing how you could try to, if you were working on a process technology that allowed you to do polysilicon both ways, so you could decide whether you want vertical poly or horizontal poly, then you could do a much more compact layout design. You can see the one on the bottom, it's doing the exact same function, but in a very different design for layout. It's almost as if you had rotated the layout and then squished things around, and you can see it's about half the area of the one on top, but it will actually do the exact same function as the layout on top. So this is just a kind of giving you a glimpse of how you can do very creative layouts sometimes to reduce the area of a given logical function. Now in practice, the one on the bottom, in most modern, as far as I'm aware, modern process technologies don't allow you to do poly pitch, vertical and horizontal, and you don't get to decide. You can only do vertical. So personally, I don't think I would ever wind up doing the one on the bottom. But if you were on a process technology from some vendor that allowed you to do that, and area was your most critical factor, it's kind of interesting to kind of try and figure out how that's working versus the one on the top, if you're interested in those sorts of things. So this is showing the clever layout that I mentioned from the previous foil, just showing a color version, and it's basically just explaining it a little bit different. Again, mentioning how it's using wider transistors, so the really wide green NMOS and the really wide yellow PMOS here. So this is kind of, like I said, if you had rotated the layout that we normally do, where PMOS is on top and NMOS is on bottom, here PMOS is to the right. The really wide devices that you see there are the carry in to carry out path, whereas the narrower devices are going from, basically to the sum out, and we care most about having a fast path from carry in to carry out. Here, it says you can eliminate the output inverters if you're trying to do, carry out bar instead of just carry out. This, if you want to examine this in more detail, it's a little bit easier seeing it in color version, and that way it's easier to see where the diffusion is versus the gates and the metal. And I think the pink is a metal 2, whereas the more bluish is a metal 1. So you can use this to examine this particular circuit maybe a little bit easier than the one from the previous slide. So here's a third type of full adder design. This is called complementary pass transistor logic, CPL. And this, in comparison to the previous two that we were looking at, can be slightly faster, but it has the trade-off of slightly more area than the previous design that we were looking at, the full adder 2 design. And the reason for that is a combination of sizing of the transistors plus just the way the connections in this, there's a lot of cross connections, and you have A, B, and C plus A bar, B bar, C bar. The routing plus the transistor sizing combination just causes a larger amount of area required in order to get your sum out and your carry out. So depending on what you're trying to trade off, if you're okay with more area but faster, then this could be a good trade-off for you. This is the last full adder design that we're going to talk about at the moment. This fourth design here is what's called dual rail domino. Domino we'll talk in more detail in a future week, but just to summarize, domino can be very fast, but it tends to be very power hungry. Usually at this point in generations of process technology, the power hungry is usually the more significant part. It can be larger as well, but the power is what usually is more limiting in today's technology generations. But it can be used for some applications, in particular like multipliers, where you need to do a lot of multiplication very fast. And in some applications, there's some usages where power is not a concern for some people, and so they'll design in a dual rail domino technology such as this. So another thing to note about this type of design is as far as the delay goes compared to a non-domino design, just typically the other designs might be, for the carry path, might have somewhere around 2 to 3 inverter delays. So if we call an inverter delay our basic unit of delay, a fan-out 4 inverter. So if a normal previous versions of the adders are 2 to 3 inverter delays, this one might be on the order of 1.5 inverter delays, so it could be anywhere from 25% faster to almost twice as fast as some of the previous full adder designs that we talked about in the previous foils.